like to invite now Dr. Cosimo Inserra, who is the winner of the Winton A Award. He's going to talk to us on exploring the brightest supernova explosions. Dr. Inserra.
Thank you very much.
I'll give you 5 minutes.
Perfect. Okay, so on the contrary in the previous talk, there will not be nice pictures. There will be no nice videos. So the best picture you can see is this one. Try to remember it. You will not see something better. So as the title suggests, I'm going to introduce you to the brightest of the supernova explosion. But before doing that, I would like to brush up my and possibly our knowledge on supernova explosion, just to go further to the brightest among them. So the explosion of a star happened to this phenomenon that is called supernova, and there are generally two main mechanisms that can actually trigger a supernova explosion. The one depicted on the left is what we call a thermonuclear explosion, where a white dwarf explodes, almost reaching the Chandrasekhar limit because it gets material from a companion star, or it collides with another white dwarf exploding as a thermonuclear explosion. On the other hand, the second viable channel is the explosion of a single star or in a star in a binary system that exhausted all the fuel, and all the layers, all the material of the star will eventually collapse in a matter of seconds on the core, releasing a tremendous amount of energy, causing its explosion. And this kind of explosion is called core collapse supernova. As you can guess, there are several different kinds of stars. We have red supergiant, blue supergiant, Wolf-Rayet of different natures. And each one of them, they will lead to a different supernova explosion with different signatures. Such signatures are mainly the electromagnetic spectrum and the light curves. With light curves is what we usually refer to the evolution of the luminosity after such explosion, in which there will happen the explosion, it will reach a maximum luminosity we usually refer as phase 0, and it will eventually fade down with different patterns due to different explosion mechanisms over hundreds of days or even over years. Sometimes just this happens in just only some weeks. So 8 years ago, astronomers discovered a new kind of supernova explosion that it was brighter than anything else, and with a lot of imagination, they decided to call them Superluminous Supernova. So we will have twice super in the front. It sounded cool at the time. So in this diagram, that is just luminosity, absolute luminosity at the maximum light versus the time that you need such luminosity to rise to the peak, you see that this is the nucleus of what all the supernovae have been known for hundreds of years, and these are, it said, the nucleus of superluminous supernovae. They are a factor 5 to 100 times brighter than normal core collapse supernova and also normal thermonuclear supernovae, and they can actually reach the maximum light in a similar time scale, but also of a factor of 3 lower. So why do we care about these superluminous supernovae? It is just because they're bright? More or less. So the fact that they're bright is very important because it means they can be observed up to high redshift that we cannot explore with any other kind of supernova now and even in the future. And that means that there are excellent astrophysical laboratories of high redshift universe. In addition, as all the other supernova explosions, they will have important information for the chemical enrichment and the stellar evolution. But there have been also some studies to connect these superluminous supernovae to the production of some kind of gamma ray burst. And least but not the last are, of course, ideal targets for current generation survey and even new generation surveys like Euclid, the ESA Euclid mission, or the Large Synoptic Sky Telescope, also known as LSST, because they are bright and they are very, very slow, so are easy target to get from ground telescope. So, but what is a superluminous supernova? How can we define it? Has anything to do with the two explosions that I just mentioned before? A little bit, but not properly. So one of the first definitions to define a superluminous supernova, it has to be a supernova that is brighter than -21 as absolute magnitudes. As you can guess, that is a very peculiar number. It is completely biased, but at that time, with a couple of objects, it was as good a definition as any to start to pick up these objects and study them as small samples. But the most important part is that the luminosity evolution cannot be explained with both the core collapse scenario and the thermonuclear scenario. So the mechanism in play to justify such luminosity was something else. The other interesting aspect of this superluminous supernova is that they were basically found, all of them, in very faint galaxy. At any kind of redshift, there was no redshift evolution from 0.1 up to redshift 2. Possibly even up to redshift 4. There have been claimed to superluminous supernova up to redshift 4. So that is a very new field because everything started in 2010. So what do we know so far? Usually supernova knowledge, it is not as fast as the supernova event itself. We get a lot of years to build a little bit of knowledge on what's going on over there. And the main question to answer at the beginning were, what is the mechanism responsible for such luminosity? And how are these supernovae linked somehow to normal kind of a supernova explosion, and how? So this is actually what we were dealing with. This is a light curves of a superluminous supernova. It's the luminosity evolution compared to a luminosity evolution of thermonuclear core collapse supernovae. Here you can actually see the 100 times factor brighter and the 3 times factors lower than any other kind of supernova that actually allow us to follow up for more time than usual supernova. But despite that, we were very, very lucky because in the first 3 years, we actually answered to both the questions that I just mentioned. And in part was because there was a lot of effort to all the scientists around the world to propose several models to explain such luminosity. And in a study of 2013, my group and I were able to create the first small sample of such object and try all the different models, creating semi-analytical models about all the theories. And we found that these light curves, this luminosity evolution of this superluminous supernova with the black dots, if you can see here the data, were very nicely reproduced by what we define a central engine model. What does it mean? It means that there is an additional energy to a normal supernova explosion. These supernovae are not something completely new. These are just core collapse supernova explosion, but they have a secondary energy source given by a central engine. And this central engine was a very fast spinning, highly magnetic, with a magnetic field of 10 to the 14 Gauss, Newton star that is called magnetar. With this scenario, so core collapse plus magnetar energy injection, we were able basically to explain almost all the observables that we usually measure in supernovae. And that actually gave us, for the first time, information about the energy of the explosion, the mass of the material expelled during this explosion that was actually no different at all with normal core collapse explosion. And, of course, since everything was matching perfectly, details of the mechanism. However, these results, although important, I always said they have to be taken with a glimpse of salt, because we all reproduce that with a semi-analytical model, and the more data we have, the more question we have, and more difficulty to explain everything in an homogeneous way. So I would say that this is the most popular model, and is a very good starting point. So the next step was to understand how these were connected with normal core collapse. And that actually, as I said before, came also in the first 3 years. As you can see, these are the electromagnetic spectrum of different objects. The 3 in the middle are spectra of these superluminous supernovae, showing some kind of elements. They are mostly iron elements. And these 2, the top and the bottom, are actually spectra of normal core collapse supernovae, but delayed of 30 days in their evolution. So that means that these superluminous supernovae, these are the spectra taken after maximum light, roughly 30 days after maximum light, while these are normal core collapse supernovae taken around maximum light. These actually delay in their evolution is most likely due to the magnetar that actually press the material and compress the material, causing a different kind of evolution and slowing down the normal evolution the supernova would have. So You can guess. Okay, first years, you almost solve all your questions. So what did you do the last 5 years? You were there playing, oh, we are so cool, we solved everything. Luckily not, even though that was tempting. Because more data means always more questions, because we will start to have more information on any kind of level. And what we actually discovered is that these superluminous supernovae are not unique, are not one kind. There are at least 3 different flavors of superluminous supernovae. Someone with hydrogen in their spectra and someone without. Those without hydrogen are the most frequent, and they were the first one that were discovered. But also among them, we found there were a lot of them clustering along this group with a relatively slow evolution in their light curves, and others, like these green squares, clustering with a slower evolution compared to the other. So one of the first idea was, since all of them, all the observables again are reproducible with this magnetar scenario, most likely the difference in the light curve evolution is due to mass. Because generally in supernovae, the maximum luminosity is due by the energy injection or the mechanism responsible for the explosion, while the width of this luminosity evolution is due to mass. However, we soon realized that this guess, although it was easy to make, it is wrong, and is not the difference between these kind of superluminous supernovae. It's not due to mass. But I will come back to that in a moment. So, as I said before, 5 years have passed from answering our first question. They were in 2013, but as you can see, that actually did not diminish the number, the interest in this field and the number of publications that have been since then, with an average of 90 to 100 publications per year mentioning or referring to superluminous supernova, making them the only transient candidate rivaling with the electromagnetic counterparts of gravitational waves in terms of interest in the time domain astronomy. But before going ahead and show you a couple of the avenue of current research on superluminous supernova, because there are so many that I would need more than 2 hours, and most likely I will bore you to death to show all of them, I want to stress the fact that in all the 8 years, we were able to reach almost 70 of these superluminous supernovae, with half of them with a decent follow-up. Although this number could look small, for supernova people, this is very high, because a lot of core collapse supernovae that have been around for more than 50 years have less of 70 well-sampled objects. And it took us 50 years to get it, while now we have, in 8 years, we add more of these supernovae than normal kind of supernova. This actually tells you about the interest that has been going on this object. But since now we have more data, we have a better knowledge on what kind of mechanism could be responsible and what are the observables of them, we could try now to redefine them in a more statistical way, in a more sensible way, using the physics and the evolution, with respect to just say, oh, it is everything brighter than minus 21 magnitude. So what we have done in Southampton, my group and I, have actually tried to define an hypersurface that define exclusively all the superluminous supernova events, and it has a very small contribution by any other supernova events or any other kind of transients like AGN or tidal disruption events or anything else you can think about it. So what we did, it was best to create a 2-dimensional plot of a 4-dimensional hypersurface. And the 2-dimensional plot is basically something that gives you information about 2 quantities and their evolution. So on the left, we have luminosity on the y-axis versus luminosity evolution. And here we have color versus color after 30 days, that actually the 2 of them together, they give the color evolution. And what we did, it was actually approach that with the Bayesian statistics and create these curved boundary that are the part of the hypersurface that describe only and exclusively superluminous supernovae and no other object. All the other supernovae, they lies over here or over here, as well as AGN, they will be over there or over there, as well as tidal disruption event. Of course, you have a little bit of contamination, but it is less than 5%, which is statistically significant for more than 2 sigma, basically at 2 sigma level. So with that in mind, now we can face and we can try to understand what a superluminous supernova is without having a mixed bag of events and different kind of physics. And this is important for this part. These are the three of the scientific avenue that I want to highlight, and because I think they are quite important, especially for UK astronomers. One of that is investigating the geometry of these events, and that could be done only to spectropolarimetric observation. Unfortunately, this kind of technique is very time-consuming and time-expensive because you need a very high signal-to-noise spectra of roughly 400 of signal-to-noise that you could achieve with 3 hours of integration at the VLT. So asking for a lot of time at the VLT is challenging. And so far, we only got information for 2 of these objects because these superluminous supernova, although very bright, they are not very close. So usually the closest one were around 0.1. That means they are not so bright in the observed frame, but they're only bright in the rest frame. So what we actually saw is that the distribution of the material of this explosion was axisymmetric. And the more we were digging inside this material and we were actually exploring the inner part of this material ejected, the more such axisymmetry was pronounced. And that matched again with an explosion injection, an injection of energy that has to be axisymmetric. And what else you could think about, again, a magnetar, because it's an axis, and you can actually inject the energy in a perfect way. And this actually was the first time we had show a link between this kind of superluminous supernovae and a peculiar kind of gamma ray bursts that are called ultra-long gamma ray bursts, that they should share the same mechanism with the same geometry. However, I told you that there are just really few examples. There are 2, and the second one was achieved only this year, and they are all the same kind of superluminous supernova. They are the one that they have a luminosity evolution that is very slow. We have no idea how is the geometry of the first one that are actually the one that are the more frequent around, frequent in the universe. Another one is that since now we have 70 superluminous supernova and even a little bit more, if you include all the data from all the surveys, we can finally start to have analysis of sample and statistical analysis. So another study that I've been done with the people in Southampton is actually they use some technique from the machine learning community and approach from a statistical point of view the diversity paradigm that I showed you before in the light curves evolution. And what we found it was that if you combine the information about the spectroscopy, that is actually the velocity on which this material is expelled into the cosmos after the explosion, with the light curve evolution and the color evolution, you will see that there are 3 supernovae that are very, very nearby together, and all the other they're spread with different luminosity decline and different colors, but all with the velocity that is double the one of these of the other. I will spare you the statistical / technical details. It took me a couple of days to figure out how they are actually working, but this is actually statistical significance, the existence of 2 populations of superluminous supernova. So the mass was not the reply, and we have now dealing with 2 different populations of superluminous supernova that maybe, only maybe, they have the same mechanism, but for sure, if they have the same mechanism, we will have to face a different progenitor scenario for the 2 of them, because we have to explain somehow such difference. But this is important because these fast are the ones that I said they are the most frequent, but the most frequent among the superluminous. They have 10 to the minus 5 less frequent than thermonuclear supernovae that are the ones that have been used in the Nobel study and have been used in cosmology. So we have take that always with a relative matter. But if you take the fast, you could actually try to standardize them in a similar fashion that have been done for type 1a supernovae. So that was actually one of the first, or one of the other questions that we had at the beginning when we discovered these supernovae. We say, okay, these are super bright, they are in very faint galaxy, that means very faint background, with a background that doesn't vary with redshift, so there is no such systematic dependencies. So if we can figure out how to use them, how to standardize them, if they are standardizable, we could use them in cosmology. So one of my first efforts in this field was try to find such a relation, and we found a tentative relation in 2014, but we had very few data. And today we have almost 3 times the amount of data of 4 years ago, and with my surprise, to be honest, but it was an happy surprise, we found a similar, the relation was still holding, and the statistical coefficient and the scatter were basically were always the same. Actually, the statistical Pearson test was even higher than it was before. So that means that if we were able to isolate this fast superluminous supernova, which now we know we can do, we can open a new era of cosmology with supernovae. And that is what we stand right now with the Supernova Dark Energy Survey Working Group. We have actually produced the first preliminary Hubble diagram with superluminous supernovae that reach redshift 2, and we found an omega matter value that is comparable with the 2 studies of the 2 most recent and most famous study of 1A cosmology that are these is the one named JLA with a lot of type 1A supernova up to redshift 1, and this is with the Hubble diagram program of Adam Rees, where it reached 1.42, and this actually is the limit of type 1A cosmology with current generation telescope. And with the superluminous supernova, we found a omega matter value that I cannot reveal to you the number because I cannot, otherwise they will kill me. I mean, this figure yesterday was completely different, and I will say, no, you cannot say that. You can neither show the error. So, okay. I will just say we found it. And these we will most likely appear later this year. But this is actually not the end. It's actually the beginning of superluminous supernova cosmology, because the new generation of telescope survey, they will give us a unique stream of superluminous supernovae. A researcher at the ICG of Portsmouth, they actually predict that there would be 10,000 superluminous supernovae found by LSST up to redshift 2.5, where again type 1A will be up to 1.5. But the study that I led with the Euclid team actually showed that the rate from the Euclid Deep Survey will get superluminous supernova up to redshift 3.5, getting a small but very nice tail stretching towards redshift 6 that will actually match with W first. And this will be the redshift, is the redshift gap that we had between the type 1A omega matter results and the one coming from WMAP and Planck. So this will be the first time we could explore this redshift range in cosmology with supernova probes. So to sum up, there are just 3 easy take-home messages. So as you can see, there will be a lot of this superluminous supernova going on, especially thanks to the latest results that they're using in cosmology, that now we can almost safely say, yes, we can, and it's not more subjected to a question mark. And despite that, we are finally approaching an area in which statistical analysis, especially if we start to have Bayesian statistics and machine learning, so an analysis that is without any prior knowledge, are starting to be very important because they will finally give us more information about the physics and reveal us if the magnetar scenario is the correct one and on what extent, if there is something else going on or is just the magnetar injection and how this injection happens, because that is another thing we still don't know. And of course, to use them as cosmological probes or in general probes, since they're still great astrophysical laboratory up to IZ. That's all. Should have been in time.
Perfecto. Open for questions. Yes, Richard. Yeah.
Oh, very nice talk.
Thank you.
You mentioned that the superluminous events only occur in subluminous galaxies.
Yes.
Presumably that's something to do with the gas phase metallicity, but I can't see what would differentiate those objects from the objects in the more massive galaxies.
So
are there any ideas?
Yeah, it's been debated for now 8 years. So there are people that suggest that the low metallicity, but of course not zero metallicity, It's a metallicity about the small Magellanic Cloud is needed to the explosion of this event, while others they suggested that you need instead a high specific star formation rate. Most likely the reply lies between these two reasons. And as you said, there is no reason why we should not see in brighter or more matter-rich galaxy. And actually this year we got for the first time a superluminous supernova that was in a completely solar metallicity, and it was very nearby. So it was 0.03 redshift. And the things is that it was from the slow group. And I could tell you that the slow group has a lot, these low superluminous supernova have a lot of other factors that I didn't want to include to avoid any confusion. But there is a third mechanism in that one.
Time for one more question. Yes, Ian.
You present them as though these are a discrete, separate, as a discrete group different from others. Would you not expect a continuous variation, and have you not seen supernovae in between your superluminous and ordinary 1H?
So there are some supernovae in between the superluminous and the normal supernovae. And that is my knowledge is that, I mean, what I believe is that most likely is still, if we believe this magnetar scenario, is always the magnetar that instead of releasing the energy at a certain time with a certain amount, he has the injection of energy that is happened a little bit slower and is less. So it will give you to a less luminosity level than these superluminous supernovae. But so far we have been found way less than the superluminous supernova, and basically we don't have any spectroscopic evolution. So we always get one spectrum, is a blue hot continuum, which is basically everything. It's just a 15,000 to 20,000 Kelvin continuum with no line. So we have no idea what's going on. And after that, usually all these guys decline in 7 days. So they boom and disappear. So most likely this is why. So this possibly is less material with a different time of injection of this magnetar, or it's something else. But there is such a continuous, but it is not completely discrete. But in terms of evolution of object, yes, there is.
Okay, thank you very much. We should thank our speaker again.
So we'll bring with me the glass and I will